Chapter 32 kind of brings a lot of things together that we've been talking about up to this point. And so it's the culmination sort of what we've been talking about with electricity and magnetism. And the title is called Maxwell's Equations. But we start off reminding ourselves here about Gauss's law, that integral E dot dA equals enclosed charge over epsilon naught. So this is Gauss's law for electric flux. So basically, this integral E dot dA is a measure of the electric flux. So that is the electric flux, and it is the integral of the electric field dotted into the area. So the electric field through some area. Now, we had mentioned sort of in passing magnetic flux integral B dot dA. So that is magnetic flux. But if you go across an entire enclosed area, so this is an enclosed area, magnetic fields go in and out, and so the total is going to be zero. So this is Gauss's law for magnetic fields. Basically, what we have here are electric monopoles. The electric monopole, that'd be a plus or a minus charge. And so the net of that, now if you have a dipole, so in other words, if you've got a sphere here and you have a dipole in here, so one's positive, one's negative, then the net flux is zero. Yes, there's an electric field in here, but the electric field's coming out one side, going in the other side. What Gauss's law for magnetic fields is telling us is there are in fact no magnetic monopoles. There's not a magnetic north pole and a separate magnetic south pole that you always find the two together. You take a magnet that has a north and south pole and you break it in half, and now you have two small magnets with north and south poles. A electric coil that's creating magnetic field becomes a magnetic dipole. And so this is the expression here for these two things: Gauss's law of electric fields, Gauss's law of magnetic fields. Well, again, there's nothing special right there. Okay, this is just a statement there are no magnetic monopoles. And then we have Faraday's law. Faraday's law says that the integral of E dot ds, this is going to be equal to minus the rate of change of the magnetic flux. Okay, so the rate of change of magnetic flux. So this is Faraday's law. And so we've got this expression down. We did several examples of this. So this is equal to minus rate of change of magnetic flux. And so there we have Faraday's law. Okay. And then Ampere's law was the integral of B dot ds, and that was equal to mu naught I. Okay. And that's I through the surface. So, okay. So by enclosed. All right. So now we have Ampere's law. And everything looks fine. And this is where things were looking just fine, except that the Gauss's law was pretty symmetric. Ampere's law, and Faraday's law, but because both of them integral of field dot ds. Now, this is where it became a little bit confusing for physicists, because this one is the rate of change of flux, and this is the flow of charge. So there's a slight difference here that was a little bit difficult to reconcile. This is where Scottish physicist James Clerk Maxwell in the 1800s was looking at this and realizing that there's an asymmetry in here that didn't make sense. And so why would one equation be a little bit different than the other. Well, he got to thinking about it, and he thought about it in terms of a wire. And so we have a wire, and it's charging a capacitor, and we have a capacitor here, and we got a wire here, and we got current flowing in the wire. And he says the current, if you're a long ways away from the capacitor, the current is making a magnetic field around here. And so we get a magnetic field, and we know that that magnetic field is the integral of B dot ds is mu naught I. And so the magnetic field is going to be mu naught I divided by 2 pi r. Okay, and that's fine. And that's going to be the case here, it's going to be the case here, the case here, the case here. Okay, but what if you have you want to find the magnetic field right there? Well, if this capacitor is very close together, then if you move a few millimeters this way, you've got a magnetic field. If you move a few millimeters that way, you get a magnetic field. So what about right there? Does it actually make sense that you have a constant magnetic field up here, you got a gap for a couple millimeters, and you have a constant magnetic field? That doesn't make sense, because you could also imagine that the current here is creating magnetic fields both forward and aft a little bit, not straight in front, but that's not straight in front right here. And right here, that's almost it's almost at right angles, so you expect a pretty sizable magnetic field there. So how do you explain that? Well, he explains that by imagining that through here we have something called displacement current. And so he defines something called displacement current. The displacement current is going to be the equivalent of a current running through here. And that displacement current is going to act like it's going to be some sort of sort of fictional current. There's no actual current that flows in a capacitor. We always talk about charging capacitor, and we talk about the current flow in the capacitor. Really, it flows here, charges, flows away there, and so forth. So there's not really any charges moving through the capacitor. We just pretend it does. So we define the displacement. So what he does is he rewrites this integral B dot ds to be mu naught I enclosed plus mu naught I displacement current. Okay. Well, what is this displacement current? And he starts thinking about it and says, well, what is really changing inside of the capacitor? Well, what's really changing in there is an electric field. Okay. And so he looks at that and says, well, that electric field that's in there, that's going to be related to what? Well, it's going to be related to the charge in the capacitor, right? Okay, so we know that capacitance is Q over V. Okay, so the electric field, or the V, is going to be Q over C, right? And so the V is going to be E times D. So that's Q over C. And he thinks about it and says, well, that means that C is epsilon naught A over D. So that means it will be D epsilon naught A. Divide like that. Okay, and then multiply by the A. So E times A is going to be Q over epsilon naught. And he looks at that and says, no, wait a minute. Let's multiply again. Epsilon naught. So epsilon naught EA is going to be Q. So epsilon naught E times A is going to be Q. Well, this is epsilon naught times the electric flux is Q. Well, remember this displacement current? Okay, what is current? That's dQ dt. So he says that the displacement current, so this Q is the Q that's going into the capacitor. So you're charging it, that Q is the charge going onto the capacitor. So the current is going to be dq dt. So if you divide, rather take derivative here, this would be epsilon naught dq, or rather d phi dt. Okay, well, let's look back at this Ampere. The only modification he did to Ampere's law was the integral b dot ds. Okay, Ampere said this is mu naught times I, and he inserted the mu naught I displacement also. So this is the actual current right there. That's the displacement current. Well, we now know that displacement current is going to be epsilon naught times the derivative of the flux. And so you plug that in, we got integral b dot ds equals mu naught I plus mu naught epsilon naught, the rate of change of the electric flux. Now, compare this with Faraday's law, which we've already talked about. So Faraday's law was integral E dot ds equals minus the rate of change of magnetic flux. Now we have integral E dot, or the B dot ds, integral B dot ds, and that's equal to mu naught I plus mu naught epsilon naught, rate of change of electric flux. And now we have a symmetry between the two. We have the integral of the field dot ds is equal to some constant times the rate of change of flux, okay, of the other field. So the electric field dot ds, integral of that is minus 1 is the constant times the rate of change of magnetic flux. Integral b dot ds is going to be proportionate to mu naught epsilon naught, those are both constants, times the rate of change of the electric flux, plus mu naught I. Now, where's the mu naught I come in? That is mu naught times the number of charges per second. Well, there are no magnetic charges per second, so that means that the term that would be, you could put a 0 up here to indicate the rate of change of magnetic charges. There are no magnetic charges, so that's obviously 0. So that makes these two equations now symmetric with each other. We've got Gauss's law for electric fields. We've got Gauss's law for magnetic fields. We've got Faraday's law. And we've got, well, Ampere's law that's modified by Maxwell, so we sometimes call it the Ampere Maxwell Law. Now, these equations collectively we call Maxwell's equations, even though Maxwell did not come up with any of them, and all he did was he added one term to an equation that Andre Ampere had come up with. And he basically came up with that one term sort of, you know, because he needed to have another current in there that wasn't an actual physical current. And so, but that was his brilliance, was realizing that it really does fit in there. Now, the reason we call these Maxwell's equations is we can now use these equations to calculate a lot of things about electromagnetism. And so that's where we'll be heading from now on.